So recently, there has been a lot of issues on carbon emissions due to issues with environmental stuff as well as our health issues. Um, there's a lot of introduction about it, about what it has been doing. Well, but the carbon emissions, but it has been coming from a lot of activities, which are electricity generation, industrialization, transportation, and several others. But the intent of this project seeks to focus on just a few of some factors that lead to the carbon emission. So with the carbon emission, there's a couple of effects, as I said earlier, which are the environmental and health effects. And with the environmental effects, it traps heat, which results in climate change. With the climate change, it usually sometimes leads to rise of sea levels in certain places that leads to flooding, as well as with the health effects, it traps smog and air pollution, resulting in respiratory diseases. So now to the focus of this project. So this project seeks to determine the effects of certain economic factors, as I explained earlier, and the outcome variable is the carbon emission itself. The predicted variables are the electricity, households, percentage growth, GDP, population, and agriculture. So these are the economic factors which I based my project on. So this is the workflow. So the workflow will be data preparation, under which we have exploratory data analysis, the modeling and evaluation, conclusion and recommendations. So this is the data. So the data preparation I imported. I didn't bring all of them here, but I imported the data, each of them one after the other, cleaned them, and I performed a summary statistics on them. So this was the outcome. So looking at the data, we have access to electricity percentage has a lot of missing data. Agriculture has 26, which household percentage has a maximum of 57 lost data. Population has 2, carbon emission has 27. So in all, it means that population household percentage has a lot of missing data, because that means it took a longer time for them to start taking data on carbon household percentage. It wasn't something which was considered earlier until latter part they realized that maybe the activities of even households with their increase in monetary activities, because the more like economic sound people become, they tend to live certain lifestyle, like buying vehicles, buying a lot of gadgets and all that, which leads to a lot of consumption of electricity, as well as maybe there'll be a lot of traveling as well, because they have enough money. So that traveling as well, that's through transportation, which can also lead to increase in carbon emissions. So with a correlation, I don't know if it's that clear, but I'll first talk about the p-value first. With a p-value, it has agriculture, GDP, population to be highly significant. That of household percentage is not that significant. It's not significant. Okay, so that is the part for the p-value. So talking about the correlation between the variables, I'll consider that of carbon emission first. The correlation between the predicted variables and that of the outcome variable, which is just a second. So that is over here. So when you check agriculture and that of carbon emission, there's a correlation, but it's not that much as compared to that of agriculture, GDP, and that of population. Among these variables as well, there are kind of correlation among them, which is when you check here, when you check GDP and that of agriculture, you can see there's a high correlation, that is 0.80. And when you check population and that of agriculture, it is 0.98. When you check GDP and that of population as well, that's 0.75, which means that there's kind of multicollinearity among these variables. So I don't want to encounter any multicollinearity, so I have to take, that means most of them are measuring the same thing. So I needed to take the ones which are measuring the same thing out to be able to model the data. And with this, I considered taking away agriculture and that of population. With agriculture, the reason why I took agriculture instead of GDP was because agriculture is something which also what contributes to the increase in GDP of a country. So I took that one out. So this is the univariate plotting that I did. So this is a representation of just one of the variables that I did, and this one was carbon emission, and it was seriously like negatively skewed. So after I realized I need to transform it before I can use it. So I did a transformation on it, and after transforming it became a normal distribution here, and the same applies to what is displayed out there, but I didn't display them each of them. So after that, I did multivariate. With that one, this was what I had from GDP, and the same thing applied to what the variables which were included. After applying the log function to it, this is what I got. So this is the modeling pattern. So two forms of equation were used. I used a simple model and that of the complex model. So with a simple model, I used access to electricity percentage and GDP for the simple part, but that one was without the log transformation. And with the complex part, I used all of the variables which were left after taking the ones which would have contributed to multicollinearity out without the log function. And after that, I applied a log function to do the same thing. So these were the outcomes. So for the simple model, this is the one without log function. So this was the outcome. I realized that when there is no log function applied to it, GDP is the only one which is significant among all of them. And also looking at their estimate, a unit increase in the GDP leads to 3.9, which is 0 point something, which is very, very minimal. So after applying the log function to it, I realized that almost all of the predictor variables that are, two of the predictor variables that were left were significant, which is the log electricity and that of GDP. When you check the estimate, previously in the when I has not applied the log function to it, it was 0.003 point something, but with this time around, it was a unit increase in GDP lead to 1.00 something of increase in carbon emission. That of access to electricity, there was another increase of 0.345. That means after the log function, that's why I was getting these figures. So that means the data needed to be transformed to be able to work perfectly. This is for the complex model. So with the complex model, without the log transformation, I realized that two of them were significant. That is the GDP and that of the household percentage. But the significance level of the GDP was way more than that of the household percentage. But when you check the estimate, a unit increase in household percentage led to a high increase in that of carbon emission, which is 6.214, but times 10 raised to the power 4, which means it's really, really high. But in the previous correlation, it didn't say household percentage was that of significance, so that means it draws an attention to it. So why is it that it's having such a high estimate over here? So after applying the log function, now it took it to 0.33, which was not like in that case when it was when I had not applied the log function to it. So that means after applying the log function, the radar was corrected that error that I would have encountered. So looking at the time that I applied the log function to the complex model as well, I found out that all the predictor variables were significant, of which household percentage and that of GDP were highly significant, followed by the last, which is the access to electricity. With their estimate and a unit increase to access to electricity leads to 0.33 increase in that of carbon emission. A unit increase in GDP led to 1.012 of carbon emission, and a unit increase in household percentage led to 0.33. And just like it's close to the value that access to electricity did as compared to carbon emission. So I'll talk about the residuals, but let me go back and talk about the residual for the simple model before going to the complex. So with the residual for the simple model, when I had not applied the log function, it was significant, right? 2.2 raised to the power negative 16, which means it was significant. Also, 80%, like it was able to explain 80%. Just a second. So it was, the model was able to explain 80% of variation in the data. When I applied the log functions to it, the model was able to explain 94% variation in the data that was used. With a complex model, when the log function was not applied to it, it was able to explain 80% of variation in data used. When I applied the log function to it, it was able to explain 95%, which means after applying the log function, the amount of data that was able to explain in that of complex and that of simple model were kind of almost the same. There's not any big margin, which means there's a likelihood of even simple model being able to do the work without the need of complex model. So these were the plot. This is the first residual plot that I did with the simple model. This was what it was when I had not applied the log function, and this was what was the outcome after applying the log function. With a complex model, this was what it was when I had not applied, and this is what it became after applying the log function. So with a QQ plot, it was like this, and after I applied the log function, this is what I got. With a complex was the same, just like what I said earlier with comparing their residuals, and the same thing occurred with the QQ plots. There's no difference in their shapes, meaning that it's almost the same as just the simple model is just the same as that of the complex model. So this is the interaction model of which I said I might have a problem. So it wasn't clear here. Well, there's kind of the extent difference a little bit, which means here there's the dots here are darker, but the ones over here kind of light, which means they are not highly interreacted. When you come to this one, after applying the log function, this one is different. So this one is this one was between the carbon emission, the household growth, and that of access to electricity. This one was electricity and household. So it was the same thing, but kind of it behaved differently. I don't know why. And this was the one that I did between GDP and that of household percentage. With this one, there wasn't any interaction that much. Kind of it started darker here, and getting to this part, it became lighter, which means it transformed from a darker place to a lighter place. It doesn't show much interaction, just that it was just maybe it was switching from this part to this place. That's what I can say about it. Okay, so for the likelihood test, it doesn't say it's significant. That means the simple model is better than nothing as compared to that of the complex model. The model fit matrix, with this one, when you check out the R squared, they're almost the same. So the values here, when you check the p-value, it means the simple model is highly significant as compared to that of it's way better than nothing as compared to the complex model, which makes the simple model better to be used, if even not without considering the complex model. With the cross validation, it was to justify which model performed better after we used a test data. So I used tenfold to do that. I didn't bring the code here, but when I did it, this was the outcome. So when you check the median, it was almost the same, 0.619. This one's 0.613, which is not a vast difference. That means they're almost the same. That means I could have still used just the simple model without using the complex model. So this was what the outcome of the model used were consistent, because there weren't any huge difference, which would have maybe recommended for maybe I have to rather use complex model or not. But it was almost the same. That means it would have been the same if I had not even considered the complex model.